To begin our conversation about the standard normal distribution, we are first going to start with an example that is uniformly distributed. Suppose that the wait times at a security checkpoint are uniformly distributed between 2 and 7 minutes. The resulting histogram shows that we have the data evenly distributed between 2 and 7 minutes where each bar is the same height. If we focus just on the area of this histogram, we know that this would be equal to 100% of our data. Now let's focus on that rectangle. The area of the rectangle is equal to length times width. The area of the rectangle is equal to 1 because 100% of the data for that histogram is included in that rectangle. The length of the histogram is the distance from 2 to 7. We have a length of 5, and the width is unknown, or you can think of this as the height. We don't actually know what this width or height of that rectangle is equal to, but we can solve for that by using our formula area equals length times width. So if we divide both sides of this equation by 5, we find that the width or height is equal to 1/5, which is also equal to 0.2. That tells us that 20% of people had to wait between 2 and 3 minutes. 20% had to wait between 3 and 4 minutes, and so on. Now, suppose that we wanted to find the probability that someone would have a wait time between 3.5 minutes and 5.25 minutes. That is the rectangle that is shaded from 3.5 to 5.25 along the horizontal axis, and then shaded all the way up to 0.2, since that's what we found to be the probability. We can find that probability or that area of that rectangle by multiplying, again, length times width for the rectangle that we're now interested in. The length of this rectangle is the distance from 3.5 to 5.25, which would be 1.75. And the width of that rectangle, or the height, would be 0.2. And we would multiply those together to find a probability of 0.35. So there's a probability of 0.35 that someone would have a wait time between 3.5 and 5.25 minutes. In a uniform distribution, we can find probabilities by using area of a rectangle. If we would like to find the area or probability using a normal distribution, we cannot use the same methods as we previously used with the uniform distribution. There is not a rectangle to be found here where we can calculate area based upon that rectangle. So we need to use some other methods related to z-scores. The standard normal distribution is the normal distribution with two key characteristics. The mean is equal to 0, and the standard deviation is equal to 1. This is the standard normal distribution. The mean is equal to 0, and the standard deviation is equal to 1. It just so happens that these values are also z-scores. So for example, the number 1 would also have a z-score of 1 because that is one standard deviation from the mean. There are some values that we already know as far as area is concerned on this normal distribution. For example, we already know from the empirical rule that approximately 68% of the data is between -1 and +1. But what if we wanted to know this area? What's the area to the left of the z-score, -1.64? Or you can again think of this as probability. What's the probability that a data value would have a z-score of -1.64? To find that answer, we would need to either use calculus or use the table that's provided. This is the standard normal table. It's also referred to as the z-score table. On this table, you can find two different types of values. Along the top and the middle, you find z-scores. The values that are in the center part of the table are areas and probabilities. And the little pictures at the top tell us that we are always shading the area to the left of the z-score that we're looking for. So this table is always going to be giving us the cumulative area or probability to the left of that particular z-score, whether we're looking on the left-hand side of the table at negative z-scores or on the right-hand side of the table at positive z-scores. We are always going to be given the cumulative area or probability to the left. So back to our example, if we have a z-score of -1.64 and would like to know the area to the left of that z-score. We could look at our table and we would start with the z-score. We're going to be over here on the left side of the table because these are our negative z-scores. So we'll start down here at negative 1.6. So we're going to focus in on this row to start with. And then we're going to grab that second decimal place, which was 4, negative 1.64. So we use this column and find where those values intersect. So the z-score of negative 1.64 intersects in this value. And let's zoom in on that. This value that we just found here is again an area or a probability, 0.0505. So this area down here would be 0.0505, or we can call this 5.05%. Let's try that again. Here's a z-score of 0.73, and we would like to find the area to the left of that z-score. We look at the table, and we go down to 0.7, and then the second decimal place was a 3. Where those column and rows intersect is the value that we're looking for. And this is our area or probability, 0.7673. And again, we can think of this as 76.73% as well. If we wanted to know the area on the other side of the distribution, the area to the right of the z-score 0.73, what we could do is we could take 100% and subtract 76.73%. Since these two areas together must add up to 100. That comes out to be 26.27%. Another way of doing that same thing would be to take 1 and subtract 0.7673. So if we think of this in probability format, then we're subtracting 1 minus 0.7673, which gives us 0.2627. So depending on whether you want this in a probability or percentage format, either of those answers would be true. Now let's suppose you wanted to find the area between two given z-scores. To find this area, we'll start by finding the area to the left of the rightmost z-score. So let's find the area to the left of z equals 2.14. On our table, we go down to 2.1 and then over to find our area of 0.9838. So the area shaded here to the left of z equals 2.14 is 0.9838, but this is not the area that we're looking for. The next step is to find the area to the left of negative 0.91. Negative 0.91 gives us an area of 0.1814. This area is 0.1814. Now that we have these two areas, we can subtract these areas to find the area in the center, which is the value that we were looking for. So we can subtract 0.9838 minus 0.1814, and that will give us the area that we were looking for. So the area between the two z-scores is equal to 0.8024, or 80.24%. Now let's look at this in the opposite way. In this case, we know that the area to the left of our z-score is 75%, and we're looking for the z-score that would correspond with that particular area. When we go to the table, remember we're looking at an area of 75%, not a z-score of 0.75. The area of 75% can also be thought of as the probability 0.75, or you can think of it as 0.7500 is the number that we're looking for on our table. So we look through all of the area values and we try to find the one that is closest to 0.7500. We want to narrow this down to the value that is the closest to 0.7500. In this case, that would be 0.7486. Then we work backwards from that value to find the corresponding z-score. In this case, the z-score would be 0.67. So our z-score here would be 0.67. Now suppose we want to find the z-score that corresponds with the area to the right of 17%. There's two ways to look for this value on our table. One is to start by looking up 17%. If we look for 17% in the area section of our table, we find the closest value to be 0.1711, and the corresponding z-score would then be negative 0.9 If we look at our picture though, we know that this cannot have a negative z-score because this z-score is clearly on the right side of the mean. The z-score that we just found is if we were to have 17% to the left, then that would be a z-score of negative 0.95. But we're looking for the z-score that must be positive. So we know from the fact that the normal distribution is symmetric, the z-score we are looking for would be positive 0.95. Another way to do this is to think about the area to the left of the z-score. Since 17% is the area to the right, then the area to the left must be equal to 83%. So on our table, we could actually go look up 83% for the area. The area of 83% is closest to 0.8289. The z-score associated with that area would be 0.95. We're still getting the same value that we got when we did this by looking up 17%, but in this case, the z-score would be positive. So no matter what method you use, you should end up with a z-score of 0.95. Just remember that the area on the table is always going to be area to the left.